So, welcome back for the second lecture in the series of charges. And first one, I define what are the charges, what was the history, and today I'll talk to you about the Coulomb's law. Coulomb was an engineer in West Indies, okay, just like Lara and others, same place. Anyway, must have been an Englishman, because they were the one who were the real sovereigns in West Indies at that time, and he was a military engineer. Okay. Coulomb's, he made an extensive study of charges and their behavior. The charge has a unit called Coulomb, whereas the basic unit, as we know, is E is equal to 1.6 into 10 to the power of minus 19 Coulomb. Okay, no, not here, please come here. Okay, so Mr. Coulomb is here, right? As I told you, all units, they are with small name, it's not with capital letters, the name, and but the unit is taken as capital letters. So this is the basic unit. Well, whether plus E or minus E, okay, minus is the unit, the basic charge in an electron, plus E is the basic charge in a proton. But remember, electron was discovered in 1897, proton later, neutron in 1932. So there was no question for Coulomb to know that the matter constituted electrons, protons and neutrons. Anyway, there must have been a unit at that time, whatever unit. Then later on, when we found, we discovered electron, the negatively charged constituent of any atom, all atoms, from the time of Big Bang theory, okay, they must have been there. Then, well, the Coulomb is a very big charge. For example, if you believe that the basic unit, the electron charge is minus 1.6 into 10 to the power of minus 19 Coulomb, okay, so let us calculate how many electrons make minus 1 Coulomb of charge. So what I have to do is, I have to just divide 1 Coulomb by 1.6 into 10 to the power of minus 19 coulombs, which turns out to be 6.25 into 10 to the power of 18 electrons. How many zeros are there? 18. Okay. So it's a very large, huge number. It cannot be if there is an electron gas in this big room. This is quite a big room. It cannot be accommodated in this big room. Anyway, but the charges that we often talk about is microcoulomb, nanocoulomb, picocoulomb, femtocoulomb, etc. Micro is 10 to the power of minus 6, 10 to the power of minus 9, 10 to the power of minus 12, etc. Okay. Now 1 Coulomb is basically defined as 1 ampere second. Okay. A Coulomb is not a basic unit of charge. I'm sorry, basic electrical unit. Ampere is. This ampere is a basic unit, just like meter, kilogram, second, and then we found that the temperature in Kelvin, these are some of the basic units in the MKS or SI system of units. So 6.25 into 10 to the power of plus 18 electrons. So a nano coulomb will have 6.25 into 10 to the power of 9, and a micro coulomb will have this into 10 to the power of 12 electrons. That is a million. Okay, that is 1,000 billion. Okay, 10 to the power of 12. Anyway, this is one of the things. So basic unit of current that we'll define later on is ampere. So 1 coulomb is equal to 1 ampere into second. Okay, because we'll see that the electric current is defined as charge divided by time. Shortly you will be very well versed with those things. But right now I need your attention, because my words carry more meaning than whatever I have written out here. Okay. Another point which I want to emphasize about the charges is that the charges are discrete in nature, just like the steps of a staircase. Okay. 1 into the basic charge, 2 into the basic charge, 3 into the basic charge, 4 into the basic charge, like that. Okay. But normally we deal in units like this: nanocoulombs or microcoulombs. Millicoulombs is also a very large, huge amount of charge. So we deal in these values, and they are as if the level that we are talking about is macroscopic. So the variation, if you add an electron or a proton to whatever is the charge over there, then the charge may increase or decrease. How much? By 1 basic charge. So therefore, even though the charges are considered to be discrete in nature, there is a quantization of charge, as I talked to you in the last lecture. Okay, we consider those charges at the microscopic level to be continuous charges, a continuous variation that is there. Okay, and another factor is that if I have an isolated space, 3-dimensional space, and we put inside a few thousand or a few million charges of different kinds. There is only 2 kinds. Okay, and another particle that we can put is neutron. Okay, so an atom or a neutron or anything like that, then the total charge is constant. It is conserved. So that we say that charge can neither be created nor destroyed, which in Arabic I told you is ma khalaq or ma fana. Cannot create, you cannot destroy. Okay. Now, this man, Coulomb, he was a very painstaking engineer, and he conducted hundreds and thousands sets of experiments, and the experiment was almost of the kind that we had in the case of gravitational verification, okay, for the gravitational force, which was in the Newtonian law of gravitation. Okay, that there was an experiment which I just forget about that name, slipping from my mind. I'm an old man, but you can always say that this is the experiment which relates to the experiment which has been conducted. Okay, now let us take 2 charges. Mr. 1 and Mr. 2. And these charges are held at a distance r apart. Okay. Mr. 1 may change well. Mr. 2 may change well. And their distance between the two of them may also change well. So they are variables. No problem. But right now I am going to take the values as Q1 and Q2. If this is plus and this is plus, both of them are plus, positive charge. Of whatever value, it doesn't matter. Or negative. One of them charges, maybe one is, charge number 1 is much larger as compared to charge number 2. Doesn't matter. Then what happens is, or it may be otherwise, or the two of them may be equal in magnitude. No problem. What happens is that there is, because they are both positive, and it was also found by the 600 BC, that charges of the same kind, they repel each other, charges of opposite kind, they attract each other. So we can see, I've just shown to you two forces. Here, the force on body 1 due to body 2. The same language I used in the case of Newton's law of gravitation. There I had m1 and m2, two variables, and r was the distance between them. Of course, somebody can ask me, somebody can ask you, how they are held at that distance apart. Then the answer is, they are held by our imagination. What in Arabic they say, Wallah alam bis sawab, I don't know. Okay, please consider it momentarily that they are held together, and the distance between them at this certain moment of time is r. Okay. So this I call F12, and this I name F21. Force on body 2 due to body 1. The same logic applies in this case also, except for, of course, the r is here, which is a variable. Okay, I have Q1 and Q2, they are also variables. The force is F12, it is towards the other charge, F21, which is towards this charge. The force acts along the line joining these two charges. Okay. Like before, the charge on body 1, magnitude of the charge on body 1 may be much larger as compared to the magnitude of charge this, but the forces will be equal. The forces will be opposite. Okay. Whether it is the case of repulsion, okay, or the case of attraction, where they say, come on, uduno minni, come on, I love you. And here they say, barra, keep away. Well, this is the situation. So, Mr. Coulomb, as we'll see, that if we look at the magnitude of these forces, maybe the magnitude of this force is F12, F21, F12, F21, and if I write, then I'll get the equation that this is a system. Okay? We'll call it an isolated system. There are only two charges in the entire space of our imagination. There are only two charges here also. Okay, nothing else. Not even me and not even you. So consider this system, and then what was found and what was deliberated by Mr. Coulomb was that the force of attraction or repulsion because of these two charges, the magnitude of that is proportional to the magnitude of Q1, is proportional to the magnitude of Q2, and is a function of R. And in the case of Newton's law of gravitation, this was a function of, and this was proportional, the force was proportional to 1 upon R square, which is inverse square law. Yes, the inverse square law holds in this case also, which I show you in the next slide. So, well, what I forgot was the name was Cavendish, and the experiment was there, and he experimentally established the inverse square law, which I told you in the case of the gravitational discussion about Newton's law of gravitation, that I could explain the inverse square law in terms of secular behavior, okay, which means that there are no preferred directions, etc. I'll talk to you about that again. Now, look here, one thing I forgot to tell you, another thing, one about the Cavendish experiment, but our gentleman Coulomb, he made very large number of experiments, repeated, and that is the scientific way of doing things. He didn't believe himself. He didn't believe himself to an authority. Like all scientists, they don't have to say that this, because I have said so, it is true. No. This is the nature of science, that we give an explanation, but we are not claiming ourselves to be an authority, and this was established by Al-Hasan, the great Arab scientist, who always said that whatever I say, please confirm it yourself. That's your duty. Okay. This is the scientific method. Now, I told you that these are two charges like this, put here and here, Q1 and Q2, positive or negative, whatever. But one thing I must tell you, that our charges under our discussion are point charges, which are spherical in shape, with the radius tending to 0, and 1 upon radius, which is curvature, tending to infinity, because curvature into the radius of curvature is equal to 1. That's how we define it. Now, we had forces F12, F21. So let us say that let the magnitude of the force F12 be equal to F12, just like that, it's positive value. Magnitude of F21 is equal to F21, and the two forces magnitudes are equal to each other, F12 and F21, which is equal to, let's say, in Urdu, Hindi, मान लिया that is equal to F. But what we see and achieve for the isolated systems that we have described here and here, that F12 plus F21 is equal to 0. There is no force from outside. Okay, like in the case of the gravitational explanation also, I said F12 is plus F21 is equal to 0, which shows that F12 is equal to minus F21, or F21 is equal to minus F21, and these notations are indicate that we are talking about the quantities with direction, that is, they are vector quantities. No problem. Now, with the massive experiments that were carried out by Mr. Coulomb established naturally by keeping two of these variables as constants, and the variables are Q1, variables are Q2, variable is R, okay, and of course F is also a variable. Well, there is another thing, another item which is important, and that is that the experiment was carried out in air, okay. So when we have, as I told you in the function of many variables, okay, that putting together the mathematical consistency tells us that this variable on the left hand side will be proportional to the product of all these three variables. So Q1 multiplied by Q2 multiplied by 1 upon R squared. Let me finish it, then I will tell you that in some texts, some of the gentlemen and of course fair ladies who write the books and teach you, they say that, let us say that F is proportional to Q1, Q2. Well, sometimes they say F is proportional to the, like this, okay, and F is proportional to 1 upon R square, and then they write this equation. But whether in the case of Newton's law of gravitation, or in the case of Coulomb's law, or in the case of luminosities, this kind of relation is there where the inverse square law is there. I don't subscribe to what my learned colleagues they do. I just say that this kind of an approach is misleading to the students. But never argue with them. Never say that Mr. Hasan Shahid taught, because Mr. Hasan Shahid is no authority. Okay? I don't know if they are or not. So anyway, so F is proportional to the product Q1, Q2 into 1 upon R square, and F therefore is equal to a constant times Q1, Q2 upon R square. This constant I am writing as 1 upon 4 pi epsilon naught, where epsilon naught is approximately equal to the epsilon for air, and it is called the permittivity of free space. How much, and this will be called permittivity of air, permittivity of oxygen, nitrogen, this, that, etc., etc., permittivity of water, this, that, like that. Okay, it all depends upon that. But the permittivity of free space, which is given a name vacuum, free space, which is given a name something called nothing. Okay, this value turns out to be, in the SI system that we have, 8.854 into 10 to the power of minus 12 Coulomb square per Newton per meter square. Okay. But the interesting feature is that 1 upon 4 pi epsilon naught, this has a very friendly value. Friendly in the sense that if you use that value maybe 10 times, okay, then you remember that. 9 into 10 to the power 9. Oh, beauty. Okay. Let me, I will finish it at this point, and then I will explain these things in the next lecture. In the systems approach, we'll draw graphs between the force and Q1, force and Q2, force and 1 upon R square, force and R. And we'll see as to how things vary. It's just a gimmick that I will share with you. But I must tell you something. When I was a student, then the system of units that was there was the CGS system. Centimeter, ground second system. And there were two unit systems, ESU and EMU, used for electric quantities and magnetic quantities. Okay. And in those cases, this 1 upon 4 pi epsilon naught, this 4 pi factor was missing. Then there was a big conference, rationalization of units, and the SI or MK system was introduced, and it was finally adapted, and today the unit is System International or International System of Units, which is meter, kilogram, second system. So remember friends, these charges which we have taken, their size is much smaller as compared to the distance between them. Okay, and of course extended bodies, the behavior and the distribution of charges, etc. is different, and we always try to give you extended bodies and try to see if you understand how the distribution takes place over there, etc. But here we have taken a very systematic approach in which we constrain ourselves to the medium, which is of course free space, something called nothing or vacuum, and in that case with the help of mathematical consistency, by the findings of course I tell you that even the value of epsilon naught is experimentally determined value. Just when I finish off, then I will tell you that there is one Mr. Epsilon naught and there is one Mr. mu naught. Okay. Mr. Epsilon naught is called permittivity of free space, and mu naught is called permeability of free space. This is what you use in the magnetic quantities, and these two friends together, they are related to the speed of electromagnetic waves. So there is a beautiful relation which encompasses these three things. We'll talk about that later on. So thank you very much. Thank you very much.